cs407, Numerical Analysis, Section 5.1, Numerical Integration. So last time in Section 4.3 we covered the process of derivatives via numerical methods. This time we're going to take a look at integration. So the chapter begins, like most of the chapters in the text, with a example that's from a real-world engineering problem. And this one's electrical field theory. The magnetic field induced by a current flowing in a circular loop of wire has the following intensity, h of x, where I is the current, r is the radius of the loop, and x is the distance from the center to the point where the magnetic intensity is being computed. If I, r, and x are given, we have a pretty formidable integral to evaluate. I think you'd agree with that just taking a look at it. It's an elliptical integral, and it's not representable or expressible in terms of familiar functions. But we can actually compute h fairly precisely using numerical methods. So, for example, if I was 15.3, r was 120, and x was equal to 84, then we might be able to calculate the value of h at 1.3355661135, accurate to 9 decimal places thanks to the magic of numerical methods. Today we'll look at our first such technique, the Trapezoid Method. One of the main mathematical procedures that is the focus of elementary calculus is integration, which is examined from the standpoint of numerical mathematics. So let's begin with calculus. In calculus you learn about two types of integrals. One, definite integrals. For example, evaluate over a fixed interval to get a number. So the integral from 0 to 2 of x squared, we calculate that as 1/3 x cubed, and evaluated at 2 and subtracted, evaluated at 0, and we get a result of 8/3. Indefinite integrals we evaluate over an indeterminate interval to get a function, or rather class of functions. So there's not just one but many indefinite integrals, and these differ from each other by constants. Thus, in the example that you can see here, the integral of x squared dx, we get a result of 1/3 x cubed plus c, where c is a constant value, and the result is still an indefinite value. Actually, definite and indefinite integrals are related through the fundamental theorem of calculus. So, basically an indefinite integral is the same as an antiderivative. And an antiderivative of a function f is any function f having the property, capital F having the property that capital F prime is equal to f. So that's the antiderivative. We're doing the opposite of what we did with derivatives. So let's take a look at this fundamental theorem of calculus. Something you should know. If f is continuous on the interval ab, and capital F is an antiderivative of f, then the integral from a to b of f of x dx is the antiderivative evaluated at b minus the antiderivative valued at a. We can also relate the derivative to the integral. And this equation in bullet 2 shows that the integral must be an antiderivative, an indefinite integral of f. So, for example, consider the integral from 1 to 3 of x squared minus 2 dx. We get an evaluation x cubed over 3 minus 2x, that's the antiderivative, and we evaluate at 3 and subtract the evaluation at 1, and we get a result of 14/3. The foregoing technique for computing definite integrals is virtually the only one that's emphasized in elementary calculus. The definite integral of a function, however, also has an interpretation as area under the curve, and that's what we're going to be looking at today. So, the existence of a numerical value for a definite integral should not depend logically on our limited ability to find antiderivatives. And you don't always have a nice form. Consider this integral. The integral from 0 to 1 of e raised to the x squared dx, which does have a numerical value, it's the area under its curve, in spite of not having an elementary function f, such that f is an antiderivative there, or such that capital F prime of x is equal to e to the x squared. It does have an antiderivative, but it's in the form of capital F of x is equal to the integral 0 to x of e raised to the t squared dt, but this isn't very much help in determining the numerical value that we're after. It's not really a closed form, but let's look at how the trapezoid rule with non-uniform spacing works. The trapezoid rule takes advantage of this area under the curve, and is based on an estimation of the area under the curve using trapezoids. Moreover, it's an important ingredient in something called the Romberg algorithm that we're going to take a look at in the next section. Now, the estimation of the integral from a to b of f of x dx is approached by dividing the interval ab into several subintervals, say n of them. And then for each such partition on the interval, the partition points xi need not be uniformly spaced. Now we'll cover non-uniform and uniform spacing. But we get an estimate of the integral by the trapezoid rule, and this is denoted by t f semicolon capital P. So here it is with non-uniform spacing, and this figure shows a typical trapezoid which has the subinterval xi plus 1 as its base. So you can see down here it runs from xi to xi plus 1 at its base, and its height is on the left hand side f of xi, and on its right side it's f of xi plus 1. The area is equal to the base times the average height. So we can get this formula. And this is going to lead us to the composite trapezoid rule. But for this trapezoid, this will give us the area that this trapezoid occupies, and it'll be an approximation of the area under the curve at this part of the curve. So the total area of the trapezoid is given by the formula, the integral of a to b f of x dx is equal to 1/2 times the sum I equals 0 to n minus 1 x sub I plus 1 minus xi times f of xi plus f of xi plus 1. And that's the composite trapezoid rule for non-uniform spacing. Basically what it says is the sum of the individual applications of the basic trapezoid rule on each subinterval gives the value for the integral. Now let's look at the composite trapezoid rule with uniform spacing. In practice, the trapezoid rule is used with the uniform partition of the interval. We'll also see uniform spacing in the Romberg algorithm, which is discussed in the next section, and we keep promising that, but don't worry, we'll get there soon enough. This basically means that the division points x sub I are equally spaced, and so if h is equal to b minus a divided by n, which is the number of points, then x sub I is equal to a plus I times h. And we denote h as the step size of the process. Because xi plus 1 minus xi is equal to h, we can therefore write the trapezoid rule of f over p is equal to h divided by 2 times the sum I equals 0 to n minus 1 f of xi plus f of xi plus 1. And the composite trapezoid rule can be written in this way. Here we've expanded the summation and we've gathered similar terms in the new summation. With uniform spacing, this can be carried out fairly easily on a computer. Basically, if we wanted to integrate the function f of x is equal to e to the minus x squared on 0, 1, we would want the integral from 0 to 1 of e to the minus x squared dx. And this one can be carried out using the elementary techniques of calculus or the analytical solution. But we can carry it out numerically. And for partitions, we can take the equally spaced points in 0, 1, so p of n is equal to x0, x1, xn, where x sub I is I times h, and h is equal to 1 over n. This leads us to the pseudocode. Now, a few comments about the pseudocode may be helpful. Here we set n equals 60, and f of x is the function e raised to the x squared. Note that we only need to change one line of code in this algorithm if another n is required, and particularly here the assignment value. Second, we don't need a subscripted variable for x sub I. You'll notice this isn't subscripted. Each point is labeled x, After it has been defined and used, we don't need to save it. Next, observe that the pseudocode has been written so that only one line of code needs to be changed if we need another value of n. And after running this code, the author reports the value of the function 0.74681. This function is closely related to the error function erf of x. And using 1/2 times the square root of pi times the error function evaluated at 1, which is what this is, the author got a value of 0.74682. Most mathematical software contains some implementation of the error function. However, we're interested in learning about algorithms for approximating integrals that can only be evaluated numerically. The experiment that we just ran shows how the computer can mimic the abstract definition of the Riemann integral. Another conclusion that can be drawn from the experiment is that direct translation of a definition in a computer algorithm may leave something to be desired in terms of precision. Of course, you've already observed that throughout the course of this course. We'll soon see a more sophisticated algorithm, such as the Romberg algorithm, that's the third promise that we made for that, can improve this situation drastically. Let's take a look at another example. So here we want to compute the integral from 0 to 1 of sine x divided by x dx by using the composite trapezoid rule with 6 uniform points. Well, to do this, we begin by arranging the function values into a table, like so. Now, you'll notice here that we've assigned the value sine x over x a value of 1 at x equals 0. That's done by a consequence of the Norris theorem. The rest of them should be pretty self-explanatory, and then we calculate using the composite trapezoid rule. And that's down here. Now, the result is not accurate to all the digits shown, as might be expected, because we only used 5 subintervals. And using mathematical software, the authors got it to 0.94608. So, you know, again, it's at least accurate to 2 digits with just 5 intervals. Later, we'll see how to determine a suitable value for n so that we can get the desired accuracy using the error term. So, if f double prime, so the next task is to analyze this error incurred in using the trapezoid rule to estimate an integral. Now, if f double prime exists and is continuous on the interval ab, and if the composite trapezoid rule t with uniform spacing h is used to estimate the integral, I is equal to the integral from a to b f of x dx, then for some zeta, or I guess any darn Greek letter you prefer, in the interval ab, I minus t is equal to minus 1/12 b minus a h squared f double prime of zeta o of h squared, or which is equal to O of h squared, which is the error convergence. There's quite a long proof of this on page 206 and 207, so I'll refer the interested readers to those pages, and I'm sure you're all interested readers in addition to international people of mystery. The author also shows how to use Taylor series to represent the error term in the basic trapezoid rule using an infinite series in example 2. Instead of looking at these theoretical or alternative proofs of this fact, let's look at how we can actually apply it. So here we can apply the error formula. Now, if we use the, we want to look at how we can apply it. And our first application is going to be in predicting how small h has to be to attain the specified precision in the trapezoid rule. So consider if we want to apply the composite trapezoid rule to compute the integral from 0 to 1 of e to the minus x squared dx with an error of at most 1/2 times 10 to the 4th. How many points do we need to use? Well, the error formula from the previous slide tells us that that error formula is minus b minus a divided by 12 h squared f double prime of zeta. And we have f of x is equal to e to the minus x squared. Differentiating that, we bring down the minus 2x, which is the derivative of minus x squared, so it's minus 2x x times e to the minus x squared, and f double prime is 4x squared minus 2 times e to the minus x squared. So we want f double prime of x is going to be less than 2 on the interval 0 to 1, and the error in the absolute value is going to be no greater than 1/6 h squared. Now, we want 1/6 h squared to be less than 1/2 times 10 to the 4th, which is the greatest error we want to tolerate. And solving for h should be less than 0.01732. Now, h is equal to 1 over n, so when we solve that for n, we get n has to be greater than or 58. Greater than or equal to 58, so we need 59 or more points. This was example 3. Examples 4 and 5 are illustrations of how many subintervals are necessary to get the desired accuracy. Example 5 shows how we can use Taylor series when the terms contain an x with a negative power, and it's difficult to get a bound on the absolute value of f double prime of x. Let's take a look at the recursive trapezoid rule. Fourth promise. For the Romberg algorithm, next section, we're going to require a formula for the trapezoid rule when the interval AB is subdivided into 2 to the n equal parts. Now, by the composite trapezoid rule, we have this formula. And if we replace n by 2 to the n, then what we get is we get r of n0. And this will look similar to the differentiation that we did last time. And we're going to use that again in section 5.2. And basically it denotes the result of applying the composite trapezoid rule with 2 to the n equal subintervals. In the Romberg algorithm, it's necessary to have a means of computing Rn0 from Rn minus 1, 0, without involving unneeded computations or evaluations of f, because that's going to slow us down. We can do this by taking advantage of previously computed results. For example, R20 here utilizes the value of f at 5 points, 1, 2, 3, 4, 5, namely a plus b minus a divided by 4, a plus b minus a divided by 2, a plus 3b minus a divided by 4, and b. In computing R3, 0, we're going to need those same points, plus 4 new ones, 1, 2, 3, 4. But we keep track of those previous points, and then we don't have to recompute them, and it's going to save us some computations. So, if Rn minus 1, 0 has been computed, and Rn0 is needed to be computed, then we can use this identity to compute Rn0. It's desirable to compute this with as little additional work as possible, and that's going to give us the recursive trapezoid formula that's shown in Theorem 2. This formula allows us to compute a sequence of approximations to a definite integral using the trapezoid rule without reevaluating its integrand at points where it has already been evaluated. So, if Rn minus 1, 0 is available, then Rn0 can be computed using this formula. And we have h is equal to b minus a divided by 2n, because again, 2 to the n, because again we're using 2 to the n points. And we give a formula for R00, which is the base or the stopping case in this recursive formula. Now, let's look briefly at multiple dimensional integration. So, for simplicity, we'll illustrate the trapezoid rule on the interval 0, 1 using n plus 1 equally spaced points. Now, the step size is h is equal to 1 over n, and the composite trapezoid rule in this case is given by this formula. Or we can write it in the following way. The integral from 0 to 1 of f of x dx is the sum from I equals 0 to n c sub I times f of I over n, where c sub I is equal to 1 over 2n at the endpoints I equals 0 and n, and 1 over n otherwise. The error in this is O of h squared. So, if one is faced with a two-dimensional integration over a unit square, you can apply the trapezoid rule twice. You still have an O of h squared error. You can find the two-dimensional formula on page 212 of the text. Now, it's a mouthful, but it's by far from the worst thing we'll see in this book. In fact, this formula can be extended over k variables, with the error still staying at O of h squared. However, the downside is the level of work changes. With one variable, the complexity of this trapezoidal integration is O of n. Two variables, O of n squared. And with k variables, it's O of n to the k. That's going to get ugly real fast, and given this complexity, we're going to need to use heuristics and approximations, such as Monte Carlo methods, in order to complete things in a reasonable amount of time. So, for historical reasons, formulas for approximating definite integrals are called rules. The lower and upper sums give rise to left and right rectangle rules, the midpoint rule, trapezoid rule, and many other rules, some of which are found in the problems in subsequent chapters of this book. A large collection of these quadrature rules can be found in Abramitz and Stagg in 1964 Standard Mathematical Tables, which had its origin in the U.S. government Make Work project conducted during the Great Depression in the 1930s. That's back in the day when people were actually the computers themselves. The word quadrature has several meanings in both in mathematics and in astronomy. In the dictionary, the first mathematical meaning is the process of finding a square whose area is equal to the given area enclosed by a given curve. The general mathematical meaning of quadrature is the process of determining the area of a surface, especially one bounded by a curve. We use it primarily to mean the approximation of the area under a curve using numerical integration procedures. In the problems of this chapter, the authors have used various well-known integrals to illustrate numerical integration. Many of these integrals have been thoroughly investigated and tabulated. Examples are elliptical integrals, sine, Fresnel, logarithmic, the error function, and Bessel functions. In the real world, when one is faced with the daunting integral, the first question to raise is, has this already been studied and perhaps tabulated? First place to look is the Handbook of Mathematical Functions and Formulas, Graphs and Mathematical Tables, the one mentioned in the previous slide from Abramowitz and Stegen in 1964. In modern numerical analysis, such tables are of limited use because of the ready availability of software packages, such as MATLAB, Maple, and Mathematica. Nonetheless, on rare occasions, problems have been found in which one obtains the wrong answer when using such a package. So, next time, the authors have spent the entire section promising you the Romberg algorithm, and in the next section we're going to deliver precisely that. Stay tuned.